Pleasure to introduce Professor Raimundo Nonato Araújo dos Santos from USP. And he is going to talk about Milnor's vector field and applications.
Okay, thank you. So I proposed actually a different title for my talk. So, but on the moment there is no talk. Let me check. Acho que alguma coisa desconectou aqui. Deixa eu dar uma checadinha. Você sabe o que aconteceu aqui? Ah, acho que voltou. Ok. Presentation. Okay. Okay. So I proposed a different title, but I decided to emphasize my talk in the Milnor vector field because I think it's possible to do more interesting application for this vector field beside the equivalence of fibrations and the other stuff that actually I think Raimundo also used such a vector field. And so anyway, all the speakers that already presented here. So anyway, I will try to introduce such a vector field in my point of view in a more formal way and do at least one application, okay? So that's the purpose of my talk, introduce the Milnor vector field and some application, maybe one or two. Let's see what's going on. So anyway, let me introduce the main tools. Some of these things can be weakened. For instance, sometimes I use only smooth map here. Maybe you can just use a CK mapping anyway. So if you consider analytic map germ from Rm to Rp, sometimes I use the same notation for the germ, the representative. G from U to Rp will be a representative, and the variety is has always we have been considering is the zero locus of G, okay, and we will be considering that has a germ offset. So it is very easy to construct such a commutative diagram. And I use such a commutative diagram to get some interesting property from my point of view. So what's going on here? You just remove the zero from the target space and the variety of G. And so you can look here for the G itself. And now you project down here to the sphere, the p-1 dimensional sphere. This is the canonical projection. And such composition give you this map here that you just call psi index G, okay? So I look this mapping here actually most of the time by using such a composition. It's easy to mean to work in each part and in the end just to glue everything together. So from the diagram we get, for instance, so this is the projection. This is very well-known projection. It's called the Milnor projection in the complex and real case. Okay, several also have already worked with such mapping to get the fibration on the spheres and fibration on the ball and so on. This also from the commutative diagram we get that the singular set of psi G is included here, the singular set of G. It's the singular set here is also in the canonical way. I mean the standard critical set is the points where the Jacobian matrix has no maximal rank. And for each y in SP minus 1, you can just consider y not 0, okay? And you can scale that to get module 1 a unitary vector. But anyway, for each guy here, let's denote Ly, the open half line through y pointed to 0. So I have some picture here just to make it more geometrically. So let's think that this is y. And if you get any no 0 y, you just scale that. And you get such a picture here. And that is Ly. Okay. This is the half line. And so when you take the pre-image of y by pi, that canonical projection, you get Ly. Okay. And XL, let's denote this guy, has the pre-image of G for the half line. Of course, everything is intersected with the image. Okay. And psi G, the inverse of psi G of y. So these two guys the same, just look into the commutative diagram and let denote that has XL. Such a construction, it's very well known. It was done by Pepe, by Cisneros, several mathematicians to work in the Milnor fibration. But anyway, this time, at least in the beginning, I will not talk about Milnor fibration, okay? Just doing a construction. So that's the geometry, the geometric idea of XY, okay? So this blue dot line here is VG, the variety of G. It's possible to show that if you take the topological closure of XY, everything glue in the VG, the variety of G, okay? So that's the geometric idea. And when you move y along the image, you get a family of xy, and it will provide you a foliation, a kind of foliation of your source space, okay? And the leaves is something like exactly this way. Oh, excuse me, I saw someone. So that's the geometric idea. So when you move y in the image, okay, you get such the composition of your search space. And of course, if you wanted to work with the Milnor fibration, the tube and the sphere, the idea is look to such leaves and check the intersection with the spheres and so on. That's the basic idea. So now, this is just the basic thing, just the basic stuff to set up the notations and the things that I want to work on. So the normal space of xy, of course, if you take a regular point on xy, it will give you a tangent plane, and you can look also to the normal plane, okay, or normal space. So the normal space is, for the moment, I will just denote it this way. Omega x, it will be spanned by omega 1x, omega p minus 1x, at x, sorry, and where this y here is the image of psi g, this is missed g here, psi g of x, and of course we already know that this space here is spanned by the Jacobian matrix of psi g, okay? The same, you can look actually each omega j here has the direction of the gradient of each coordinate function of psi g. So that's also the basic things. Now I need to define two sets that we call the Milnor set, and also call it the polar variety. So, but now we consider rho x has the square of the distance function to the orange. search space, okay? And omega g, by definition, is the point in the search space where ρ is not transversal to G. So the points is where you have a tangency, okay? And the same definition for psi G, okay? Just to change here for psi G. So this is called the whole non-regular points of G and psi G, respectively, and also known as the polar varieties of G and psi G with respect to ρ. So what is a consequence of that is if X is in the polar varieties of G, you are saying that the gradient of ρx is a linear combination of the Jacobian of Gx. Okay, it's very easy, of course, because this guy is the double of X. Okay, and also use X is the polar variety of psi G if only if this guy is a linear combination of this guy. The same statement, just change the appropriate function. What else? So it's a calculus exercise. If you consider Gx this way, this is the coordinate functions of G. And of course, psi G is this function here, this mapping here. That's the coordinate function, just modulated by Gx. And the rows of Jacobian of psi G is a combination of the gradients of Gx. It's just take the calculation, take the derivatives. It's easy to check that. So the gradient of Gj over absolute value of G is a combination of the gradient of the coordinate function, the Gy's. So so what you can conclude here? You can conclude that, of course, if a point is here, you are saying that this is a point here means that the gradient of ρ is a linear combination of the omega j's, but since the omega j's is a linear combination of g's, the gradient of g, the j's, of course, you are saying that the point is here. Okay, this is a easy exercise. So the Milnor set of such a projection, the Milnor projection, the open ball, when you remove the zero locus, is included in the Milnor set of your mapping, previous map J. Okay, so it comes in the package. You don't need to do nothing. So, okay, let me just write down these things here. So, what we have? We have that. So that's U minus V. So you get here. You apply here the G to RP minus the orange here is the canonical projection. And here you get the one-dimensional sphere. This is a submersion. And here is your psi G. And we are looking to psi G has the composition of pi with G. And so we already have that the singular logs of psi G is included in the singular locus of G. Okay, And also, now we have that the Milnor set of psi G is also included in the Milnor set of G. Okay? But of course, we already know that the singular locus here is included here, and the singular locus here is included here. So we have such a diagram. Okay, this is such a square diagram. So, okay, let me just mark that here. So, okay, maybe, okay, yeah. So that's just a picture to help to understand a little bit the Milnor set. Actually, the Milnor set of G. Okay, so this black curve here is supposed to be the fiber of G over Gx. So you fix a point here, you send it to the image and take the fiber of Gx, you get such a curve here. And this red line here is supposed to be the tangent space in a regular point. We suppose that we start with a regular point. Okay, so this is the tangent plane of such a curve, the tangent the tangent line, if you want. And so if such a line here is tangent at the point x to the sphere of radius absolute value of x, okay, what we are saying? We are saying that such a red line here should be included, must be included in the tangent plane of the sphere. That's the green plane here, okay? But also here, we have such a plane here, yellow plane, which is the normal space of the fiber, okay? So if such a curve here is tangent to the sphere, you are saying that the vector position must be included in the normal space of the fiber. Okay, that's what we already discussed. This is just a geometric idea to help us to understand a little bit more. Okay, so this suppose he is not supposed to be SP minus 1. It's supposed to be N here. There is a mistake here anyway. So, but that's the geometric idea that we already discussed. Okay, maybe I will come back later for some of these pictures. So now you just consider the discriminant set of G has the image of the singular set Sing G. Just consider such a definition at the moment. Okay, so we say that G is regular whenever we can find a small enough epsilon, positive epsilon, such that the Milnor set intersect with such a guy here is empty. So now what we are doing here, we just consider a epsilon ball in the search space, and we removed the pre-image of the discriminant set. So we removed all fibers where such fiber intersect the singular set, okay, and we removed that. We are saying that a map is whole regular if such intersection here is empty for some epsilon small enough. If you get one, of course, anyone smaller than that will satisfy such a condition. So it's equivalent to say that into the epsilon ball, the Milnor set of psi G is included here. Okay? So that is our definition. There are several equivalent definitions, actually. For instance, the Cisneros, Jawad, Pepe have considered such a definition, but not in this condition. He is a little bit weak. I will explain later. What's the name he called that? Is a D regular map, right? Yeah, so it's called a D regular map. But anyway, so for such a radius, what we can say? So we can construct two vector fields which is tangent to the fiber of the fiber xy. So how we constructed that? We take the orthogonal projection in the direction of omega x, okay, on each point. We project the gradient of absolute value of g, the square of the absolute value of g, and take the projection also to the gradient of rho x. Okay, so it's the same to say, okay, take just the projection of the vector position parallel to omega x, to the tangent plane of xy. Okay, that's the idea to construct these two vector fields. And the point is that if you assume that your function is all regular, these two vector fields must be not zero. There is no singularity for such a vector field. Okay, it is easy to see because if in a point x this guy is zero, you are saying that this direction here should be included in omega x. But we already saw that omega x is a combination of the gradient of gx, and since this guy is also a combination of the gradient of gx, if this guy is included there, it should be a singular point of g. But you already removed in such a, so the point is in the complement of this guy. Okay, so it is easy to see that this guy is under such condition, this guy is not zero. And also this guy is not zero because, again, if this guy is zero, you are saying that this guy here is included in omega s, but of course you are saying that your map is whole regular. So it's a contradiction. So you get this, under such a condition, you get these two non-zero vector fields which is tangent to the xy variety. Okay, so that's the geometric idea of such a projection. Such a vertical vector here is supposed to be the omega x direction. Okay, and so what you are saying that, so this picture is true. If you are asking for whole regularity, this is the true picture. Okay, so the gradient of the square of gx should be something like this. So it's not included here. And also the gradient of rho x should be like this. It's not included here in such a directions. And when you project parallel to such a direction here, you get something like v1x here, v2x here. Okay, so that's just a geometrical interpretation of what we already discussed. So what else we can say? So if we just if you consider, of course we are saying that G here, we are assuming that G is whole regular and epsilon is such a radius. Okay, so let x here, the vectors v1, v2 are linearly independent if only if x is not here. This is also true, and this is just if you just work with such a condition, as we already discussed, you see that it's easy to prove such a result. Again, what we are saying that, okay, if the point here is not in the Milnor set, that's the true picture. Okay, that's what we are saying. So what we can say in addition? So if we get a point here, of course these two guys now should be collinear, okay, by such a characterization. And it is not hard to see that actually if a point here is here in the Milnor set of G, in the complement of this guy in the Milnor set of G, we can now decompose this guy in these two, let's say, directions. Okay, the direction of this guy and also in the direction of the omega x. This is maybe this is not so easy to understand such a decomposition, but it was done by Hansen and Brodersen. But the idea is, so if we consider the matrix given by omega 1x, omega p minus 1x, and the gradient of absolute value of gx squared, and for one side and another side, we consider this matrix here. So GPX, okay? The point is that if you look to the subspace spanned by this guy here, this row here, it's the same that the subspace is spanned by this guy. Okay, that's the point to check that if the vector position is a combination of this guy, it must be a combination of this guy as well. Okay, so that's the point to check that. It's not so hard to check, but there is just algebra linear is possible to see what is going on in this case. Okay, maybe you need a little bit more information about how is the composition of each omega j. Okay, to see that in a more easy way. But that's the point. So if the point is in the Milnor set of G, you can decompose such a direction here, which is, of course, parallel to the vector position in this way. Okay, there is a coefficient here, AX, multiplied by the gradient of absolute value of GX squared, plus some coefficient here, BJ. J here should be from 1 to p minus 1 instead of 2. Okay, so 1 to p minus 1. And AX and BJX is scalar functions. Okay, so that's the point. And now, if you look for such a decomposition, you can think the vector fields. To recover the vector fields, you just project down such a guy in the tangent plane of xy. Okay, on each side. So you have such a sum from 1 to p minus 1, p minus 1 of bjx omega j x. Okay, if you project such guy here in the tangent plane of xy, you get for the projection here is the projection is parallel to omega x. Okay, so when you project here, you get the v2x using our notation. Okay, but this should be the projection here. Okay, but of course the projection is linear. So this, what you get? You get the ax, the projection of this guy, which is v1x. But since this is parallel to omega x, the projection is 0. Okay, so that's the, you are saying that, okay, in the, if a point is in the Milnor vector, in the Milnor set of G, such two vector fields should be collinear, as we already said, and that's the coefficient of collinearity. Okay, it comes from here. So when you decompose that in the whole space, project down, you get such a coefficient of collinearity. So now the point is, okay, I want to understand a little bit more about such AX to be able to construct the Milnor vector field. Okay, that's the point. And so next step, so easily follows from one that if x here, x is in the Milnor set of now psi j, such a Milnor set we already saw that such a Milnor set is included in the Milnor set of G. Okay, so if x is here, ax is 0. It is also easy to understand because if you are saying that x in the Milnor set of psi g, okay, what you get? You are saying that so these two guys, this guy here, this direction here, and these directions here, they are linearly independent. When you are saying that this guy here is included here, of course, this should be 0. Okay? And if this guy is 0, of course, you are saying that this guy is included here. So this is easy, very easy to check. But now you have, when you decompose this guy here in the whole ambient, you have a criteria to check if your point is in the Milnor set of psi or not. That's a point. It's a geometric way to check that. Okay? This point here we already checked. So okay, let's see what we call the Milnor vector field. Okay, so let G analytic map germ. We consider M greater than P, P at least 2, and rho x again this has the square of the distance function to the origin. The same stuff as before. So a Milnor vector field for G, abbreviated by VF, is a vector field, let's say nu, here. Here, of course, we already checked that this is a good ambient to work on. Okay, satisfying what? So this guy, this vector field should be tangent to the fiber of xy. Okay, where y is the image of psi j x. Okay, and this condition, so the dual vector field dot product with the gradient of rho x must be positive. This is a condition we ask. So what we are saying here is that such a vector field must intersect it a small enough sphere in a transversal way. It should the flow goes in the position direction. Okay. So and now we also ask that this guy here, I mean the dot product here, must be positive, which says that the flow of the null should go in the direction where the square of distant function of gx is increasing. Okay, this is a good property anyway. So that's what we call the Milnor vector field. And so how we can construct the Milnor vector field using the Milnor idea. So now, since we already saw how to construct the two directions on x, y, which is v1x and v2x, we just take such a we just take such a combination here. This is called also the bisector vector field. So we normalize one, v1x, normalize the second ones, v2x, and take the sum of both. This is a natural way to construct such a vector field. And so that is the natural candidate for such a vector field. Just take the bisector vector field generated by v1 and v2. Okay? And so what we can say about these guys? So by the previous lemma, if you consider nu x this way, of course this is a Milnor vector field for G, but here, see that we removed also the Milnor set of G. Okay, so what's such a lemma claim to us is that's the lemma. So outside the Milnor set of G, these two guys they are linearly independent. Oh, sorry. So since they are linearly independent, such a combination is not zero. It's very well defined. I mean, there is no singularity for such a bisector vector field, and you are done. Okay. But of course, we want to extend such a vector field in a nice way to the Milnor set of G. That's the point. Okay. Okay. Let's just check. Okay. Maybe I will not. My talk will be a little bit short, but anyway, let's see. Okay, we are here, right? Yeah. So, of course, that we wanted to extend now to the Milnor set of G. But of course, in the complement of such bad fibers, let's say this way. Okay, let's see how we can do that. So for that we need to work with such a guy again, okay? And this construction, it was pointed out by Hansen and Brodersen, but in the case where the discriminant is only a point, the discriminant set is only the origin. But you can extend such a construction just removing the appropriate set. But anyway, so what we can say? So the following are equivalent. So there exists a Milnor vector field for G here. Now the Milnor set of G is included in the picture for some epsilon small enough. If long if AX is positive for points in the Milnor set of G. Okay. Of course, there are several things that we proved before we start such things, but the point is that if you can find any other Milnor vector field, this guy here, as we constructed this such a bisector vector field, will be also a Milnor vector field. That's one point that I will not do the details now. There is several things that we need to check. But so the point is that we just need to check the existence of the Milnor vector field for this particular vector field. Okay? I will show you the reference in the end of the talk, where you can check such a equivalence. At least there is such equivalence proved in your thesis, right, Michael? Yeah. So anyway, let's check for such a particular candidate for the Milnor vector field. So such a bisector vector field. So this is, just to remind you, it was constructed this way. It has the bisector of V1 and V2, okay? So what's the problem here? The problem is if such guy is 0 in some point, okay? But such guy 0 means it's equivalent to say that V1x is, V1x and V2x point in the opposite way, okay? This is the possibility, this is the only possibility where this guy is 0, okay? So V1x is something like beta x V2x for some negative beta, okay? And let's see that we can remove some possibilities, but not everything in the moment. So, of course, as we already remarked here, okay, you are saying that this AX would be negative, okay? I mean, if this guy is 0, this AX must be negative. So, and of course, if this guy is positive, this guy is not 0, the converse, okay? And of course, this guy, if this guy is not 0, it satisfies these 3 MJ conditions, M1, M2, M3, okay? It is tangent to the fiber, by construction. What else? The second condition, let's come back a little bit just to check. So the M1 condition is trivial. It was by construction. The M2 condition say that this guy, this dot product here must be positive. But of course, it was constructed to satisfy such a condition because when you consider the dot product between nu x and the gradient of rho x, so of course, this guy is in the tangent plane of xy. So such a dot product here, you just see what's going on for the projection of this guy in the tangent plane. But the projection of this guy in the tangent plane, we denote it by, this is the V1, right? Let's just come back to the notation. V2, sorry. This is the V2. So this is the V2x. Okay, but now this is such a combination. So you get 1 over V1x, V1x, V2x plus 1 over absolute value V2x V2x, V2x. This is the squared of absolute value of V2x. So you get 1 over V1x, V1x, V2x plus the absolute value of V2x. And if you just take this guy, put this guy in evidence, you get something like V1x over V1x, V2x over V2x plus 1. But this is the angle between V1x, V2x. And since you are saying that this guy is not pointing the opposite way, this should be greater than -1. So this must be positive. This is positive. So this is positive. So this is the standard way to check that. The same if you just change the gradient of rho x by the gradient of absolute value of gx squared. Okay. So what I'm telling you is that this guy, this is the natural way to choose such to define such a vector field, satisfying these three properties. But we also proved that if any other vector field satisfies such a condition, this vector field also should satisfy that this condition, these three conditions. So that's so this is why one of the points I think is very interesting, because maybe you can work the dynamic of this guy and apply these things also to understand a little bit about the foliation of such xy and so on. So anyway, okay, maybe. So so now some criteria for the existence of this guy. So the criteria is the criteria is to check when under the whole regularity, when this guy here is positive. Okay, that's the criteria. So one is if you again consider now a smooth map germ, just define AX a matrix AX this way, okay, and BX this way. I mean, looking this matrix here has the disposition of the vectors is in rows, and here is in column. Okay, I changed it here P by M, M by P. So here, look at this guy as column vectors. And now define dx has this product, bx and ax, this way, and take the gram matrix of ax. This is the product between ax and the disposition of ax. Okay? So using such a notation, we can prove that a pointer here, if the point x belongs to the Milnor set of G, ax has such a, you can write ax this way, the determinant of dx over the determinant of the gram matrix. Okay, and hence ax is positive if long if the determinant of dx is positive. So you can just check the determinant of this guy here is enough to get that ax is positive. So this is a criteria you can check. Okay, if someone gives you the representative of the germ, you can just construct such a matrix here, take this product, you get a squared matrix, take the determinant. That's it. Okay? This result extends a condition defined by David Massey. Maybe I do not have such a. I'll check if I have the reference here, but I think I remember the title and I can write down everything. I put it here, but I'm not sure if I put it in the end. But I can provide you if you want. So, but anyway, for the moment, forget about this guy here. And so this result extend a condition called the Milnor condition C, which was that was defined by David Massey in a paper where he was asking he was trying to prove some condition which depends on the construction of such a Milnor vector field. Okay, so but anyway, this is a more general result in some sense. And what else? So again, if you start with analytic map germ, actually we don't need analytic here, right? Yeah, it can be smooth, maybe CK. Anyway, if you just wanted to check the existence of such a vector field, see that we are not talking about any fibration, the tube or sphere. Anyway, just about the construction of such a vector field. So if you start with can be analytical, whatever you want, a map here, or the representative of a mapping, if G satisfies either the conditions, J has the same multiplicity for all J. What does it mean? It means that when you take the Taylor expansion, just look to the degree, only the degree. Doesn't matter what appear in the Taylor expansion, but the degree of the smallest degree. Okay, we are not asked that this guy is the same. Only the degree. Take the smallest degree in the Taylor expansion. If everyone is the same, or this guy here, for I different from J, the dot product is 0. This guy, they are orthogonal. Under these two conditions, we are also able to prove that AX is positive. So, for instance, if you take any analytic function, this is maybe too much here. Take any analytic function, a complex analytic function, of course you have such a condition, for instance, okay? And also, there is another class of mapping called, actually, this naming it was set by David Massey, called the simple L map. But what's the definition of the simple L map? It says simple L map is nothing less than called the harmonic morphism. So harmonic morphism, it is a mapping from Rm to Rk, okay, such that let's say f is f1, fk, such that 1, the absolute value of fj, the gradient of fj is equal to the absolute value of fy for all ij. And this guy, the dot product here, is 0 for I difference from j. So this is, by definition, a harmonic morphism. And such kind of morphism have been studied in geometry because it's possible to get minimal subvariety by looking to the levels of such functions. There are several studies about such kind of morphism. Okay, so anyway, if any harmonic morphism, what we are saying is that any harmonic morphism or a simple L map satisfies such a condition. So AX, you can construct the Milnor vector field. Okay, that's the point. So what else? So all these things, of course, much more is written in this manuscript. Geometrical conditions for the existence of a Milnor vector field. There are several other conditions, and I don't want to bother you just explain all these things. But so it will be submitted for publication. It's also possible to find it on archive. Okay, you see much more conditions that we found to guarantee the existence of the Milnor vector field. Now let's do an application of this guy. Okay, an application is in the color that we call the equivalence of the Milnor-Hamm fibrations. Okay, so let me introduce one of the called the Milnor-Hamm fibration. So we say that the discriminant disk G is radial if has a germ offset at the origin. It is a union of real half lines or just the origin. Okay, this is well known in some sense definition. Okay, maybe I need okay, so if you look to this projection now, this is supposed to be psi G. I missed a G here. Okay, sorry about that. So now if you look to this projection psi G, which is called also the Milnor projection, if you ask that the discriminant is radial, such a projection is well defined. Remember that the fibers here, how we construct the fibers here? We just took the vector position, the half line, and put back by G to get the fibers of psi G in any unit vector here. So since you are asking this guy is radial, when you take the pre-image here, you are removing all the fibers which will be projected by psi G, on this guy. So this is very well defined if you ask for radial radial map, radial discriminant, sorry. So that's the lemma. Just so if G, if you consider G analytic map germ, or you can also ask it has a smooth, or doesn't matter. What we did here does not matter if it is analytic, smooth anyway. With a radial discriminant, then this guy is well defined. Okay. What is the colored Milnor-Hamm sphere fibration? So let G be an analytic map germ. If the restriction 4 is a locally trivial smooth fibration, that I mean, we are asking that this is a trivial, locally trivial, sorry, smooth fibration in the ordinary sense. Okay. So under this condition, if such a fibration, if you have such a fibration, if you have such a fibration for any small enough epsilon, you say that it is a Milnor-Hamm sphere fibration. So what we are saying that actually we are asking that such a fibration exists for any small enough epsilon, and also we want that such a fibration, I mean, all those vibration when you move epsilon get small. I mean, when epsilon gets small and small, it should be equivalent. Okay, such a vibration should not depend on epsilon. So anyway, now consider such a, we call the extended transversality condition. Okay, so this is the Milnor set of G. We remove the pre-image of the discriminant set and take the topological closure. Now intersect with VG, and we are asking that such intersection is included here. Okay, it's only the origin. Okay, it could be empty anyway, but it's included in such a set. Okay, only such a set is just composed by, it's a unitary set. Okay, only the origin. So anyway, that's the picture in such a case. So that's the pre-image. So here we are looking to epsilon ball for epsilon is small enough. Okay, and in this red set here is supposed to be the pre-image of the discriminant set. So it may intersect. So it's supposed to have the zero set of G, of course. Okay, and it is, I mean, the zero set of G is included in such a guy, and that's the geometric way to see that. Okay, maybe such guy here has several components, several leaves like that. Okay, but anyway, under such a extended transversality condition, what we are saying? We are saying that we are able to get a kind of Hoare or conical neighborhood here, okay, included V, but of course we remove V and you remove this guy here, okay, remove the pre-image of this guy. And it's such that, let me move to the next picture. Here, these red lines here is supposed to be the fiber of psi G, but now intersected the sphere. Each fiber now in the intersection of such a conical neighborhood with the sphere, we intersect here transversally, which means that in such a neighborhood here, the intersection of such a neighborhood in the sphere, you get subimation for psi G. That's the point. Okay? on such an certain intersection, your map psi G will be sublimation. That's the idea. Maybe it's a little bit hard to see this guy, but if you, for instance, look to the case where the discriminant set is only the origin, that's what that's the picture. I mean, the picture becomes a little bit better to understand, but it's the same in such a case. Okay. So anyway, I don't want to give too much detail detail now. Just to I'm just stated the result here. One of the results we got concerning the fibration, the sphere fibration. So if you have an analytic mapping here with such a radial discriminant and satisfying the condition 5, if G is regular, then such map, the psi G, will be the projection of a fibration. I mean, we have a Milnor-Hamm sphere fibration. Okay, such a psi G. Okay, I mean we get the definition. That's the point. So so the classical case is when disk G is 0, and it was studied by John Milnor, for instance. The complex case, in the real case, he was not considering the projection given by G over absolute value of G received to the sphere, but that first step here, you can use it to get what is called the NS pair or open book structure on the sphere provided by a map with such a condition and, of course, something else, okay, under our extended condition. In the Milnor case, Milnor just asked that the mapping here has isolated critical point. Of course, everything works well if you have isolated critical point. E.g., such a condition is satisfied, and also the extended condition will be satisfied because if you have isolated critical point, we already know that the tone AF condition or AG condition will be satisfied along the zero locus, and this is what the tone AG condition implies such a condition. It is easy to understand. Such a transversality close for all small enough for all sphere of radius is small enough. That's the point. But anyway, so others mathematicians already studied that, like Jacquemart and who was Ceade Verjovsk, by looking to a Hermitian product of a holomorph vector field. And who else? I developed also a study with Ruas in 2005, where such things, most of these things, tools and ideas started also in our study and also in this paper here, okay? So Pichon, Ceade as well for FG bar functions. Cisneiro, Molina, Seade, Snussi, and it is not updated. They have done something new more recently. Anyway, what else? For higher open book structure under transversality condition with Chen, Chiba, and so on. Several Orca, for instance, Baudin. But Baudin, it was, I think he did also something from the local case, but also in the global case, using that such a FG bar and such a FG bar mapping. And when you look at the projection of the sphere, it becomes a meromorph function. That's by Gaffney, Saeki, Souza, Hollenberger, by Massey. So he was working to get condition for a map satisfies, they call it the stronger Lojazevity inequality is a kind of strong Lojazevity condition, or Lojazevity inequality for real mapping. And who else? Hansen, Brodensen, and yeah. So a lot of people have developed some work in such setting. Now let me just talk very quickly about Milnor-Hamm tool fibration. I don't know if I have enough time, maybe 1 minute, or o relógio lá em cima. So é suposto terminar às 3, acho que 5 minutos acho que dá para. Só vou dar So I'm just introduce very quickly another kind of fibration called the Milnor-Hamm tool fibration. There are several stuff here. I tried to get a diagonal. I'm not sure if I was successful, but anyway, if you start with analytic mapping, the set, the singular set has a germ of set is well defined, but it is known that let's say the canonical discriminant set, canonical in the sense that several people have used in such a definition, and also the image of your mapping, it may not be well defined and has a germ of set. So we need to fix these things somehow. And we say that a mapping is nice if the image of the discriminant set, actually you change a little bit the definition of the discriminant set, but when the image of the discriminant set and the image of the mapping, both are well defined and has a germ of set, we will call such a mapping a nice mapping. Okay, that's the main idea here. For instance, if you get such a mapping here, you can change here. Instead of C, you can just consider from R2 to R2. You see that the image of this mapping, when you take balls with a radius small enough, you see that the image of such a ball of course centered at the origin. And when you move the radius, take the radius small, you see that the image is here of such mapping is changing. It is not well defined as a germ of set. It's a well-known example, I think. It was surprising to us, of course, but anyway, now we could see that it is well known. Here, it was surprising somehow. I'll tell you later, because we thought that if you ask only isolated critical value, the image would be defined as a germ of set, but it's not true. It's not true. Isolated critical value means the image of the critical locus is included in the zero set. Okay? Outside the zero set, everything is regular. The image is only included in the zero locus, and your mapping, the image of your map is not well defined as a germ of set. So surround the zero set, everything is regular, but it change. It may change. This was surprising to us. In general, of course, we cannot expect that it will not be well defined. But in such a case, we would expect that, okay, in such a case it would be nice, but it's not nice. VG is intersect the singular set. No. Of course, under such a condition, it works nice. Yeah. But, when we run of such a condition, we were working, we were just trying to understand a little bit better the image of mappings that the singular set, so the singular set was included in the variety. So surrounding the variety, everything is regular. But even under such a condition, the image may not be defined as a germ of set. It was a little bit surprised it was. But anyway, for technical reason, we consider now the discriminant set of a nice map geometry this way. So now we take the closure, the topological closure of the, let's say, canonical discriminant set, and also take the union of the boundary of the topological closure of the image. Of course, such a set here may not be defined as a germ of set at the origin, of course. But when each word well defined, we need to consider that. And that's the point. Okay? I mean, if the orange does not set such a guy, it's not a problem. You just shrink the neighborhood, get rid of that. But in general, we need to consider also such a guy. So the point is that if now you consider, I use the same notation just to make it easier. But anyway, now we say that G has a Milnor-Hamm tube fibration if for any epsilon small enough that exists epsilon, which is very small if you compare with epsilon, such that now this map here is a locally trivial smooth fibration, which is independent up to diffeomorphism of the choice of the topological data. Okay? I mean, it doesn't matter if you shrink the epsilon or shrink, I mean, if you shrink epsilon and also eta satisfying such a condition, you still have a fibration and everything is diffeomorphic, is diffeomorphic up to, everything is diffeomorphic, sorry, okay? That's the point. I mean, such a fibration, the diffeomorphism type of such a fibration does not depend of such a choice of guy here. Okay, that's the point. So if you have such a fibration, you can also get such a fibration here, just taking eta small enough. Okay, you take the pre-image, you take the restriction. It is also a fibration. We call such a fibration the Milnor-Hamm. We call empty tube fibration because now there is nothing in the interior of that tube. Okay, it is empty. It's just the cover. But anyway, the point is that if G is nice with radial discriminant, and for some reason doesn't matter, you can prove that the Milnor-Hamm tube and sphere fibration both exist. For some reason, doesn't matter how you do that. Okay? If we have a Milnor vector field, they must be equivalent. That's the point. So I'll stop here. There are a lot of things to talk about, but I don't want to bore you anyway. So I'm done. Thank you.